Welcome to UVU CS3060 Lecture 5.11, where I demonstrate how to implement a scheduling algorithm. For this lecture, I'm going to implement the first come, first served scheduling algorithm. This is the simplest algorithm. It's the one that you probably could easily do, but I want to make sure everybody understands how this is done. The other three algorithms that you will be implementing will be more difficult than this one, varying orders of degrees, but I will try to give you pointers on where you need to change the code so that you can make this work for yourself. For this particular assignment, you're going to have a process list in a file, or you can send it via the standard in. I will provide all the code for reading from a file or from standard in, so you don't need to modify that. And each particular algorithm will be in its own function, and I've provided those as well. So what we want to do to evaluate our algorithms is we want to choose some criteria, and we're going to choose three criteria. We're going to choose response time. Response time is calculated by first finding the first run time of a particular job and then subtracting from it the submit time. Please note that the submit time is provided for you. It is part of the input for the program. But the first run time needs to be found by your simulator. So you will have to write the code that finds this first run time. The second criteria is the wait time. You will find the wait time by taking the job terminate time and subtracting from it the submit time and the burst length. We discussed this in the previous video, where we discussed how to find criteria that the wait time can easily be found by subtracting the burst length by the total turnaround time of that particular job. Speaking of turnaround time, that is the third criteria that we're looking at. You calculate the turnaround time by subtracting from the job terminate time the submit time. You'll note that turnaround time, job terminate time minus submit time, is also part of the wait time. So it is likely in your best interest to calculate the turnaround time and then subtract burst length from that turnaround time. Now do remember, submit time and burst length are values that are already provided for you for each job. So you do not have to write a simulator to generate these. Just simply take the input values that you're given. The two pieces of information you need to have is first run time. This is the time when the job first sees CPU time. So in the case of this, the burst time hasn't changed. And then you'll calculate the job terminate time. This can only be calculated when the job has used all of its burst time. In a non-preemptive system, it only happens just after first run time. So first run time and job terminate time can be calculated at the same time, because the job will use its entire burst in one move. In a preemptive system, these may come in different areas of our simulator, and so we need to be careful of that. But you need to find the first run time and the job terminate time for each job. So if we take a look at the assignment itself, if we come down here, you'll see these are the four algorithms we're going to implement. This video will help you implement the first come, first served. Download the tar file, which contains 4 files, including the ASSN4.c file. There is some extra credit. I'm not going to cover it in this video. The description should be sufficient. But you will take the ASSN4, do not modify the main function. It does not need modified. You'll work with each job, you'll work with each function, and this is what your output should look like. And in all actuality, these strings here, such as the title and then the output, have been provided for you. The only thing you need to change is the title to the program. So make sure that you print out the title exactly as you see here, with the colon and with the title and with your name and a UVID. And then you will assign ASSN, you will submit ASSN 4.c. Clearly this needs to be corrected. So let's take a look at the terminal now. So here we are in the ASSN4 directory. All the files exist that we're going to work for. These come straight out of the tar file. I'm going to go ahead and just, we'll first take a look at the process list. Now do note that the process list, each line, at least within this file, each line consists of 2 numbers. Each line represents one burst job within that the scheduler needs to process. Each burst job has 2 parts, a submission time and a burst length. You need to account for both of those as you work with your scheduler. Remember, both statistics require that you have the burst time and the submission time. So let's go ahead and edit this. Now, first thing, make sure you have in this comment inserted your name and your UVID. And these values should match the first line of output you provide within your program. So make sure that you are replacing this line with the title and your information. With those changes made, let's just take a brief look through the rest of the main function. Again, you should not need to modify this main function, but I do want to go through it. We use standard in unless an argument is provided on the command line, at which point we open a file. Once we've opened the file, each set of 2 values is read into the submit array and into the burst array. Now submit and burst will be arrays of size max jobs, which is set to 100. So there will not be any more than 100 jobs. Once the jobs have been written and you've verified that there's more than one job, each set of jobs is sent to these 4 functions one at a time. And then the main function returns. So let's take a look at the first come first serve function. Now mind you, these are the same functions provided for you across the board. You have 3 statistics you're trying to gather: a response, a wait, and a turnaround time. Once you've run your simulator, it should be able to print out the statistics for those 3 parameters. So what you want to do is you want to cumulatively add values to response, wait, and turnaround so that it may be averaged, and that average may be printed out. So we need to change our scheduler. We need to do several things. The first thing we need to do is we need to establish a job index. So job index, this is going to be the index variable that indicates which job we are currently working on. And we need to establish a clock. Once we have those established, we want to loop through all the jobs. Remember, this is first come first serve, so we start at the first job and work our way through one at a time till we're done. Once we're inside this loop, and so I'm going to indent this comment. Once we're inside the loop, the first thing we need to do is make sure that the clock actually is pointing to a job. Again, if you remember, well, let's go back and take a look at this. If we take a look at our job list, you'll notice that the first job doesn't start at clock time 0. It actually starts at clock time 5. So before we can start our loop really, or as within our loop, we need to make sure the clock value is up to the submit time for our current job. And we will add 100 to that clock time of 5. So this first job will run from 5 milliseconds to 105 milliseconds. Job 11 will arrive while the job 1, or the first job, will be running when the second job arrives. The second job will run before 105 milliseconds. Thus, when 105 milliseconds is over, we do not need to advance the clock to match 11. 11 has already gone past. So we can start this second job at clock time 105 and run it for 20 milliseconds. That will bring us to clock time 125. Well, the third job here doesn't start till clock time 238. So again, we will move the clock time forward because our clock is not up to date with the next job we are running. So we're going to update clock as necessary. Once we've actually managed to figure out where our clock is, we're going to calculate the next event, which in our case is the job end. When the job ends, that's the next event. So we will have two values: a start time, or basically the current clock time, and then the next event time, or the end time for this particular job. Once we have the start time of a job and the terminate time of a job, we can now calculate the statistics. This is where we can add our values that we know we need to add to our variables up here, the response and wait and turnaround. Once we've gone ahead and calculated statistics, we're done with the current clock time. We can set clock to the next event time, moving our clock forward, if you will, so that we can go on to the next job. And of course, we need to increment our job. Now, at this point, we need to make sure that there is enough jobs inside the or that we've actually, for this particular algorithm, all we need to do is move the increment the job index forward, and we should be ready to loop back up. So let's go ahead and try this. We're going to create our two variables. So let's do int job and int clock. And we're going to set both of those to 0 initially. So there we go. Now we need to create our loop. And our loop is going to be just a simple while loop. And there's one condition we're going to check. In this case, it's going to make sure that the value we have for job as we increment is less than count. So if we have 20 jobs, this should allow us to do jobs 0 through 19. So now, once we've got this, we can go ahead and test. If our clock is less than, this is the job that we're currently working on. So we want the submit time of the job. If the clock is less than the submit time for the job, let's go ahead and set the clock time to the submit time of the job. This allows it to bump forward so that it will be ready to calculate the rest of the statistics. We need to calculate the termination or the job end time for this. And really, we call this next event is equal to clock plus burst of the job. And that should give us what we need for the next event. Now we have our two values, we can calculate our statistics. So we want my response time. Now what is my response time again? Well, let's go ahead and take a look back at the so our response time is, simply put, the first run time, so it's that clock variable, minus the submit time. All right, so let's go ahead and do that. My response time is the clock time minus the submit time for the job. Now I need to do let's go ahead and look for the next statistic. It's wait time. Wait time is the job terminate time, or the next event, minus submit time minus burst length. So let's go ahead and do that. My wait. And actually, if you remember, I said that the wait time is actually a value that can use the turnaround time. So let's calculate the turnaround time first. To do that, we'll just do my turnaround is equal to, and this is where the next event that we calculated comes in, because this is when the job terminates, minus the submit time minus the burst time of the job. And finally, my wait time is going to be the turnaround time minus, turnaround time is just simply next event minus submit. My turnaround is next event minus submit minus the burst. Getting ahead of myself here. So at this point, we've got our three statistics calculated. We can go ahead and accumulate this. So response is incremented by my response. Turnaround is incremented by my turnaround. And finally, wait is incremented by my wait. So I've gone ahead and incremented the statistics. Once I've gathered my statistics, now it's just a matter of setting the clock to the next time of value. So clock is equal to next event, incrementing the job plus plus, and then looping back to the top. This is the first come, first serve algorithm. All we're doing is looping through each job, getting the clock time and the next event time, getting the beginning and end events for this particular job, calculating our statistics, and then moving the clock forward and incrementing to the next job. So I'm going to go ahead and write this. I'm going to go ahead and make this. And we already have problems. Let's take a look at what our problems here are. So clearly I have syntax error on line 19, and it doesn't find clock in all the other places. So let's go ahead and fix those. So we don't need int a second time. That's kind of silly. Let's build it now and see if our changes made any difference. So on line 34, we've got a problem. Here's line 34. Clearly, I don't have a semicolon at the end of my line, so I need to fix that. Build it. And it builds successfully. All right. Now, what we're shooting for, what we're hoping to reach for our particular simulator is we're trying to get our values to look a little bit like this. If we can get 276.4, 276.4, and 448.9 out of our simulator, then we've had success. Let's see if it worked. I'm going to quit the editor. I've already made the program. I can verify it by typing make, and it will say it's up to date. I'll run ASSM4 on my process list. And if we look at our response time, the response time is 276.4, wait time is 276.4, and turnaround time is 448.9. So this currently completes the first come first serve simulator or schedule simulator. There are a couple of things you need to recognize when it comes to this particular simulator. It is extraordinarily simple. There are things you're going to need to do within shortest job first, shortest runtime first, and the round robin algorithm that first come first serve doesn't handle. The first thing that you want to consider is you want to consider how you're going to sort, or I should say bubble up, the shortest job in the ready queue. Now, two things that are very important here. You're going to have some way of modifying this queue. You're going to bubble a particular job to the top, but do remember your submit and burst times are constant arrays. You cannot change these. So you're going to have to create your own array so that you can bubble up short jobs. But you're not going to want to just simply sort all the jobs right from the get-go, because the ready queue will be changing throughout the run of your algorithm. Let's go ahead and take a look at what that means. If we take a look at the process list, at 5 milliseconds, we're going to, with shortest job first, we'll have one job, and that will run for 100 milliseconds. Now, at 105 milliseconds, we will have one job, this 11 millisecond, or the second job here, and it will run for 20. So at 125, that job terminates and there's nothing left on the queue. At time 238, there will be one job. And that job will run for 80 milliseconds. Now, when it runs for 80 milliseconds, there's going to be that's going to bring us to 318 milliseconds, which means there will be one job, this job, on the queue, which will run for 20. So that's 338. Which brings us to this job, 338. And you see that the ready queue always has different numbers of jobs. Now, as you get along, you'll actually have more than just simply one job in the ready queue. You'll have 2, possibly 3, even 4 jobs in the ready queue. You will need to move one of those jobs to the top, or select the job with the shortest burst time in order to get shortest job first to work. So you'll have to perform some sort of bubble up function to make that happen. And this is true for both shortest job first and for shortest runtime first. Before you can calculate the next event or anything, you need to bubble up a short job. Now, in addition to calculating the job end, for the job, so this is going to work just fine for shortest job first. Shortest job first has no problem taking this job and running it to completion. But for preemptive jobs, those preemptive jobs will have a next event at interrupt. But only if the interrupt happens before termination. So, next event is setting next event to clock time plus the full burst time of the job is fine for non-preemptive schedulers. But for preemptive schedulers, the job can run to its termination, and if at all possible, it should. But if there is an interrupt, there needs to be a different next event time. For example, for shortest runtime first, which is a preemptive algorithm, shortest runtime first, its interrupt happens at the clock time for the next job. So when that next job is submitted, that's when that interrupt will happen. That interrupt may happen during the runtime or the burst length of the current job, at which point the next event is the interrupt before the end of the job. If the interrupt would happen after the job, then let the job run to completion. In round robin, the interrupt is the time quantum. And for this assignment, that time quantum is 100 milliseconds. And so if the burst is longer than 100 milliseconds in round robin, the interrupt will happen. The event will happen first, and that's the only length that the job will run. Now, with preemptive jobs, you're suddenly going to be calculating these statistics at different times. You'll calculate response time at the start of a job. And that start is when the remaining burst time is still equal to the original burst time. Now, this remaining burst time is a value you're going to want to keep track of for the preemptive jobs. You'll create an array, and you'll store the original burst time in the remaining burst time spot. And then every time you have a job that is preempted, you will subtract the length that was used by that particular job before the interrupt from remaining burst, and then use that for, say, bubbling up a job. The turnaround time and wait times, these will calculate the turnaround and wait at the end of a job. And this is going to be when the remaining burst time is 0. And of course, you'll be subtracting the burst time before you figure this out. Or the remaining burst time is the same as the difference between, and you could do this, the difference between clock, our next event, and clock. And actually, if you just simply do remaining burst, remaining burst is the difference between those, because you'll get the length of time from the current clock time to the next event time. And if that burst time takes up that entire time, then you've reached the end of the event. Also, one last thing you'll want to consider is you can't just simply do a job increment. you have to, especially in, well, for all the algorithms, shortest job first, shortest remaining time first, and round robin, you'll have to fill the ready queue with arrived jobs. Remember, you use this ready queue up here when you perform the bubble sort. This ready queue tells you what jobs are currently available to be either looked through for the shortest job, or to just simply choose the top one for the round robin scheduler. So there are several things that need to be considered in the remaining algorithms. Like I said, this one, first come, first serve, can be written up very easily. Please take into consideration things as having a ready queue inside your scheduler to keep track of the jobs that have arrived and the jobs that continue to run. Please keep track of the fact that you need to keep track of the remaining burst time of jobs. That's a second array that you'll want to keep values in. Frequently, just as a hint, I will implement the ready queue as a circular list, meaning that I have a begin pointer and an end pointer. The begin pointer chases the end pointer. The end pointer tells me where I can insert a job. The begin pointer tells me the top of the list where I can simply pull off a job. Whereas the remaining burst is a one-to-one match for the burst array that is passed in. And you'll just simply copy a burst value from the original into the remaining time when that job is moved into the ready queue. So at this point, you should have enough information to complete the other three algorithms. Again, take your time. This is a fairly complicated assignment, so it will require you to put a little extra time into this to make it work. You may have heard in the past that this was a do your own assignment type of thing, or do your own language type of assignment. That has changed for this. You must use the files given to you, the C files given to you. You also, if you take a look at the assignment specifications, you will find at the bottom there are some instructions for how to get extra credit. You may form groups for this assignment, groups of no more than 3 people. Those 3 people are allowed to implement the other 3 algorithms, and you must do this by separating out those algorithms as specified in the instructions. The extra credit is a bit more complicated. It is meant to help you in a group situation, and I'm more than happy to help you through those issues when you come to them. So this brings us to the end of Lecture 5.11, where I demonstrate how to implement a scheduling algorithm.